So in this video lecture, we will be tackling our quinolones, our antibacterial quinolones, their structure-activity relationships, and their different categories. So our quinolones could be roughly divided into our older quinolones like our nalidixic acid and our newer quinolones such as our fluoroquinolones. So the main structure of our quinolones is patterned after our nalidixic acid. So our nalidixic acid will serve as the prototype for all quinolones and fluoroquinolones. The main ring structure of our quinolones and fluoroquinolones is our naphthyridine ring. So it is a bicyclic compound with 2 nitrogen atoms separately on each ring structure. So you can see our naphthyridine here. And you can see the naphthyridine but inversed in our nalidixic acid as well. So for our structure-activity relationships, the more potent analogs are sometimes classified separately as our fluoroquinolones because all members have the 6-fluoro substituent. So our older drugs are only limited to urinary tract specific agents. Usually these are used for cystitis or for our urinary tract infections. So if your quinolone does not have the 6-fluoro substituent, their use is only limited to the urinary tract. However, newer quinolones that have the 6-fluoro substituent have more activity in other types of bacteria, primarily gram-negative bacteria. Structure activity studies have shown that the 1,4-dihydro-4-oxo-3-pyridine carboxylic acid moiety is essential for antibacterial activity. And the effective antibacterial spectrum of nalidixic acid and the earlier members of the quinolone class are only limited to gram-negative bacteria, including common urinary pathogens. So as I said earlier, if your structure does not have a fluorine substituent at number 6, it won't be effective other than in urinary bacteria. So these are the different examples of our quinolones. So on the top left, you can see the parent compound or the part of the compound that exudes our antibacterial activity, our 1,4-dihydro-4-oxo-3-pyridine carboxylic acid. So you can see the structure. I will highlight it on the other parts of the structures. You can see it here, here, and here. Okay, so levofloxacin, norfloxacin, and ciprofloxacin has this 1,4-dihydro-4-oxo-3-pyridine carboxylic acid as the main part of its antibacterial activity. Now, next, we have our numbering. So we have to learn numbering so we can accurately say if each substituent is assigned properly to its number. It's because structure-activity relationships are dependent on which part of the structure a substituent is attached to. So for our numbering of our quinolones, the number starts with the nitrogen atom going towards our carboxylic acid, then towards our carbon double bond O, then going towards 6, 7, 8. Okay, so the numbering system is 1, 2, 3, 4, 5, 6, 7, 8. You are not to number these atoms. These carbons are fully bound and they will not serve any substitution purpose. That is why their numbering is skipped. You are not going to count these 2 carbon atoms. That is why it's 4, skip 5, and there is no 9 here. Okay? Next, the tip to easily find number 1, it's because sometimes you might find 2 nitrogen atoms, like in the case of gemifloxacin. How to find the first nitrogen atom is to simply look for C double bond O, and opposite that is nitrogen number 1. Okay, as you can see, C double bond O opposite nitrogen number 1. Here in our ciprofloxacin, C double bond O, opposite that is our nitrogen number 1. And C double bond O in our gemifloxacin, opposite that is our nitrogen number 1. Now, the next thing you need to know is the direction of counting. Now, once you know which is nitrogen number 1, you're going to count towards carboxylic acid. So, since carboxylic acid is going here, the count is going here. 1, 2, 3. Let's have ciprofloxacin. 1 going towards our carboxylic acid. 2, 3, 4. Again, 1 going towards our carboxylic acid. 2, 3, 4. Okay? You're not going to count the opposite direction. It's because you're going to give carboxylic acid a lower numbering, so that you're going always to count towards carboxylic acid, not away from carboxylic acid. Okay? This is wrong. Always towards carboxylic acid. So let's proceed. Now we know the numbering. So for our structure activity relationship, the pyridone system must be annulated with an aromatic ring. So this is the pyridone structure, and it only states that it must be annulated with an aromatic ring. It simply means it should have an attached aromatic ring to our pyridone. So you can see from our previous slide, you have an aromatic ring, attached to your pyridone, attached to your pyridone. Okay? So you can hardly see any quinolone which has a monocyclic structure. It's always bicyclic in nature. Next, the introduction of substituents at position 2 greatly abolishes activity. Okay, so let's find 1. 1 is here. 3 is here. 4 is here. Therefore, this is 2. You're not gonna put anything on 2 because it will decrease activity. Okay, so you should leave number 2 alone. If you can see on the practical example of ciprofloxacin, 1, 2, there is nothing on 2. That is why if you put anything on 2, it will decrease its antibacterial activity. Next SAR, positions 5, 6, and 7 and 8 of the annulated ring may be substituted with good effects. So let's count. 1, 2, 3, 4, 5, 6, 7, 8. So 5, 6, 7, 8 are all good for substitution. However, some substitutions are better than others. In particular, fluorine substitution at position 6 is associated with significantly enhanced antibacterial activity, hence the name of our fluoroquinolones. So 1, 2, 3, 4, 5, 6. Ideally, you should put a fluorine atom at number 6. Hence, you see fluorine number 6 at our ciprofloxacin. Next, alkyl substitution at the 1 position is essential for activity. Lower alkyl substituents generally having progressively greater potency. So, in the 1 position, you see 1 here, you can substitute a methyl. You can also substitute an ethyl if you want to, and you can also substitute a cyclopropyl like you can see in our ciprofloxacin. levofloxacin. Okay, so it is essential for activity, meaning it at least must have a methyl, ethyl, or cyclopropyl substituent. If it has no substituent at one, no alkyl substituent or of at one, or it might have a different substitution like an alcohol, it will lose its antibacterial activity. Okay, so alkyl substitution at one is essential for activity. Next is aryl substitution at the 1 position is also consistent with antibacterial activity with a 2,4-difluorophenyl group providing optimal potency. So you can substitute this at position 1 if you would like to do so. However, all currently used quinolones in the market do not have this substituent. So this is a nice to have substituent, but it's not currently used in any structure as of the moment. Next is newer members of the class possessing 6-fluoro and 7-piperazonyl substituents exhibit an extended spectrum of activity that includes effectiveness against additional gram-negative pathogens. Fluoro and 7-piperazonyl substituent exhibits an extended spectrum of activity that includes effectiveness against additional gram-negative pathogens. So let's have some examples, such as our ciprofloxacin, our ofloxacin, our levofloxacin, and our norfloxacin. So if you can see the fluorine atom, that is number 6. So all of this has a 6-fluoro substituent. And if you look at number 7, they also have a piperazonyl substituent as well. This means these antibiotics have greater efficacy against gram-negative bacteria. Ring condensations at the 1,8, 5,6, 6,7, and 7,8 positions also lead to active compounds. So on the screen, you can see the condensations of levofloxacin and ofloxacin. There it is at 1,8. This is also at 1,8. Okay, it does not mean that if there is condensation, it loses activity. In fact, it actually increases our antibacterial activity. Next, the incidence of CNS effects associated with the quinolones, such as irritability, tremor, sleep disorders, vertigo, anxiety, agitation, convulsions, have been attributed to the antagonism of gamma-aminobutyric acid receptors in the brain by the quinolones. Only fluoroquinolones having a 1-piperidino, a 3-aminopyrrolidino, or any similar basic moiety at the 7th position appear to have these properties. And the low incidence of the CNS effects for most quinolones is apparently because of their inability to penetrate the blood-brain barrier. Another property of the quinolone class is phototoxicity or sensitivity to sunlight. Quinolones having a halogen atom at the 8th position, such as our lomefloxacin here, this is number 8, has the highest incidence of phototoxicity. And those with an amino or methoxy at the 5 or 8 position has the lowest incidence. So here you have an amino substituent in our sparfloxacin. Okay, so lomefloxacin is notorious for phototoxicity.